Large-scale HVAC systems operate on a massive physical disconnect. A centralized chiller plant generates immense thermal capacity, but that cooling power is physically isolated from the loads distributed across the building. Bridging that gap requires an active transport layer, the chilled water pump. Its core function is converting electrical energy into the fluid velocity and pressure required to physically move that thermal mass through a complex network of piping. We are going to build this distribution network from first principles. We will examine centrifugal physics, the relationship between flow and head, the architecture of variable primary flow, and the mechanics of fluid dynamic failures. Without an engineered transport system, the thermal potential generated at the plant remains locked within the chiller's heat exchanger, unable to reach the building's airstreams. We begin with the baseline thermodynamic loop. A single chiller on one side and a single air handling unit on the other, connected by a continuous circuit of supply and return piping. Return water enters the chiller's evaporator at 12 degrees Celsius, transferring its heat to the refrigerant and exiting at a cooled supply temperature of 7 degrees. That 7-degree water travels to the AHU, absorbing heat from the warm room air blowing across the cooling coil. The water warms back to 12 degrees and returns to the chiller plant. Driving that continuous thermal cycle requires intense mechanical action. Inside the pump, an electric motor rotates the impeller. Fluid enters the center eye. Curved vanes accelerate the water radially outward at high speeds. The surrounding pump casing, known as the volute, catches this high-velocity fluid. The volute acts as a diffuser, forcing the water to slow down, which mathematically converts that kinetic energy into potential energy, or pressure head. The pump does not create cooling. It creates the localized high-pressure zone necessary to force that cooling through the resistance of the piping network. We measure a pump's capability using two primary metrics. First is flow rate, usually measured in cubic meters per hour, which tells us exactly how much thermal mass is moving. Second is head. This is the pressure energy required to overcome the total resistance of the system, the friction of the pipe rowels, control valves, cooling coils, and physical elevation changes. This graph maps the dynamic relationship between those two variables. First, we plot the system resistance. As flow rate increases through a fixed network, the friction pushing back increases exponentially. Next is the pump performance curve. As the pump attempts to deliver a higher volume, the maximum pressure head physically drops. The exact intersection is the operating point. When building demand drops, control valves at the AHUs begin to close. This creates a bottleneck, shifting the system resistance curve steeper. Because the pump curve is fixed by the impeller's geometry, the operating point is forced to slide up and to the left. Engineering an efficient transport system requires matching the mechanical pump curve to the dynamic system curve, ensuring optimal thermal delivery without wasting electrical energy. Historically, large plants faced a structural conflict. A chiller's evaporator requires a strict, constant flow of water to prevent its internal tubes from freezing. But a building requires highly variable flow as thermal loads shift throughout the day. The traditional solution is the primary-secondary piping arrangement. The primary loop's sole job is to maintain a safe, constant volume of water through the chiller. Secondary pumps act independently, varying flow to push exactly what the building demands. Modern designs consolidate this architecture into a variable primary flow, or VPF system. VPF eliminates the redundant secondary pumps entirely. It utilizes advanced controls to allow the water flow to safely vary through both the chiller and building simultaneously. While this reduces capital costs and pumping energy, it forces the system to rely on highly sensitive control logic to safely manage varying flow. That control logic relies on differential pressure, or delta P, calculated by subtracting the return water pressure from the supply water pressure at a specific location. As building valves close under low load, the supply pressure spikes. The sensor detects this and signals a variable frequency drive to lower the electrical frequency, slowing the pump down. Slowing the motor frequency leverages the pump affinity laws, which dictate that power consumption decreases by the cube of the speed reduction. This nonlinear relationship allows a small drop in motor speed to result in a massive reduction in electrical load, offering greater efficiency than mechanical throttling. However, manipulating flow and pressure has strict thermodynamic limits. The most severe systemic failure is cavitation. This occurs when the suction pressure at the pump inlet drops below the water's specific vapor pressure, which is frequently caused by blocked strainers or poorly designed suction piping. Because of the intense pressure drop, the chilled water literally boils at ambient temperatures, forming hundreds of tiny vapor bubbles within the fluid stream. These vapor bubbles are swept directly into the high-pressure zone of the rapidly spinning impeller, where they violently implode. Each implosion generates a localized shockwave. Over time, these continuous micro-impacts erode solid metal impellers, destroy mechanical seals, and generate severe mechanical vibration. Systemic fluid dynamic imbalances, or neglected resistance, frequently manifest as mechanical pump failures, which are often incorrectly attributed to manufacturing defects. To correctly manage this architecture, we have to view the entire water-cooled plant as an interconnected machine, integrating both the chilled water loop and the heat rejection side. If an air handling unit reports poor cooling performance, the diagnostic logic must follow the fluid. You verify pump flow, check supply and return temperatures across the chiller, inspect the physical coil condition, and confirm the valve positions. Simply blaming the pump for low cooling is an incomplete approach. Technicians must trace the entire thermodynamic and hydraulic chain to locate the restriction. The pump functions as a dynamic engine, modulating its mechanical output to track the shifting hydraulic requirements of the building loop. Mastering variable frequency control and accurately mapping the intersection of pump and system curves is the only way to extract the full designed capacity of a modern centralized chiller plant.